Hello AP Chemistry and welcome to 20.5 and 20.6, where we take what we've just talked about for galvanic and voltaic cells and we tie it back to thermochemistry principles and equilibrium principles, right? Which again, chapter 20 is great because we get to throw back all this stuff, right? So if as we talk about this, you're like, G, what? K, what? Go back and review that, right? Delta G is chapter 5 and 19. K is chapter 15. That would be where we introduce the concept of K. All right. So anyway, looking at our equations, right? We have our delta G equals NFE, and note that we have all these little the little degree signs, right? Which means standard, right? And when we talk about standard, what does that mean? Right. That means we are talking about 1 molar concentrations. That means we're talking about 1 atm. If we're talking about gases, it means we're talking about 298 Kelvin. And so those things are all implied when we use any of these values, right? So when we're talking about, that's why this is not, okay? And so this allows us to relate things, right? So thinking about what we know, right? We've already said that when E is positive, that means it's a spontaneous cell, right? We know that. It means it happens on its own. So we know that if E is positive, what should the value of delta G be? Right, it should be a negative value. That makes sense. And if we look at this equation, right, that flows all together, right? In that we have negative number of moles. Moles will be a positive number, right? F is this, which is also a positive number, right? Make sure you have that memorized. On your on multiple choice, you'll go ahead and estimate this as 96,500 on your multiple choice just to make your math easier. But for the free response, please do go ahead and use this whole number, okay? So anyway, we have that's positive, and this is positive, which means that if we put that negative in front, every time we have a positive E value, we should get a negative delta G. Where what does delta G tell us about? Right, that's our free energy, and when we have a negative free energy, that goes back to work, right? If we have a negative free energy, that means my system, whatever it is we're looking at, is able to do work, right? And if we think about the opposite scenario, right, obviously if we have a negative E naught value, that means we'll have a positive delta G, which means that in order for it to happen, we would have to put in that amount of work to the system in order for it to happen, yeah? Going over here and tying together G and K, right, this we talked about previously, right, where if G is negative, for example, right, that means K is going to be what? Right, K is going to be greater than 1, meaning it favors the formation of product, right? Where K is approximately, right, product over reactant, right? That's how we can think about it, right? There are exponents and other things to think about. But that's our equilibrium constant, right? That is the amount of product present at equilibrium, the amount of reactant present at equilibrium, where equilibrium is what? Right. Equilibrium is where concentrations no longer change. The rate of the forward reaction equals the rate of the reverse reaction. Therefore, macroscopically, it looks as though nothing is happening, right? So anyway, if the place where the reaction comes to rest means there is more product than reactant, means we have a negative delta G, meaning the reaction is favored in the forward direction, right? Thermodynamically favored. Here we're going to go ahead and tie together our E and our K, right? Wherein if my K value is greater than 1, meaning products are favored, that means the natural log of a value greater than 1 is what sign? Right, positive, right? The ln of a number greater than 1 is a positive number, which means that my E naught value is positive. Yes, does it make sense? All right, so make sure you know those equations so we can translate, right, between my E and my G and my K. So if we look here, right, now we can talk about non-standard conditions, right? So here, this goes back to chapter 5 and 19, where we talked about calculating delta G away from standard conditions by using Q instead of K, where Q is, right, that's an instantaneous snapshot of my concentrations, right? So Q is the same principle where we have products over reactants, right? But it's at whatever point in time we happen to be, right? Where K is always going to be equilibrium, right? That is the concentration at equilibrium. This is the concentration wherever we happen to be right now. And if we think back to the previous chapters, we compare Q versus K to figure out which direction a reaction is going to go on its way toward equilibrium, right? Because everything is headed towards equilibrium, right? Um, then so basically we take this and we take some of the equations on the other page, right, and we come up with these, which are versions of our Nernst equation, which you do need to know, okay? Which one you memorize is kind of up to you. Right here, all we've done is we've basically taken this, which is a constant, 8.314 joules per mole Kelvin, right? And we have our temperature, which when we're talking about electrochemistry, most of the time is a constant, right? And Faraday's constant, which is clearly a constant. And then we turn it into a log, which is just more sensible for most people's heads, right? And we come up with this version. But if we think about this, right, Q, right, is again the concentrations wherever we are at a given moment in time, okay? And if we think about Q for most of our voltaic cells, so if we imagine a classic voltaic cell, right, where here we have some kind of ions, here we have ions, and our electrodes, right, our salt bridge, right? But we have ions as products, and we have ions as reactants, and then we have these solid electrodes that participate or not, but they're solids, which means irrelevant to a Q or K, right? Which means that Q for most of our cells is 1, right? Where we're starting, because the concentration here is 1 molar, concentration here is 1 molar, which means Q is usually 1, right? Which means when we stray from that, we are going to change my E value. Yes, we're not changing E naught, because that's based on standards, but we're changing my E value. So if we just think, using our math sense that we know, right, when Q is greater than 1, what does that mean? Right, that means more product than reactant, yes? More product than reactant. So if we have more product and my Q is greater than 1, what does that mean? Right, that means my log of Q is going to be a positive value. And if my log Q is positive, what happens here? Right, that means we subtract that term from here, which means that my E decreases. Yes? Does that make sense? Right? Where in the alternate scenario, right, if my Q is less than 1, meaning we have more what? More reactant, that means my log Q is going to be what? Negative, right? And if log Q, if this term is negative, then if I subtract a negative, that means my E value actually goes up. Does that make sense? So if we think about that, right, if I stack it so that way there is too much product, then if we think again about the potential energy, right, there is no reason for those electrons to migrate to the other side if we've already stacked it with too much product, right? Likewise here, if we stack a reaction with too much reactant, right, then we're going to help sort of push the forward reaction. Yes? Does it make sense? All right. Which brings us to the concept of a concentration cell, right? Wherein we can have nickel ions in both sides with nickel electrodes, which if we think about what that means, right? If we think about a standard cell, what that means is the reduction reaction would have a value of x, the oxidation would be negative x, which means that overall the E value would be, right, 0, right? The E naught value would be 0 for this process. But it turns out we can make it happen without any outside energy if we set it up right. So if we look here, right, well, we'll see if this is my anode, that's where oxidation is supposed to occur, right? That's where oxidation is supposed to occur, means what reaction is happening in there, right? We are going from nickel solid to nickel plus 2 electrons, right? So oxidation is occurring here, and we'll note that what we've done is we have a really, really low concentration of nickel ions. Over here, where reduction is supposed to occur, this reaction is going to be what? Right, we're going to take nickel plus 2 electrons to give us nickel solid, right? Which means that we are going to consume those electrons there. So if we came up with an overall reaction, this would be my reactant, yes? And this would be my product ions. Yes, does that make sense? So then if we look at what my Q is going to be products, which is 1e negative 3, over my reactant, which is 1, which means that my Q value is less than 1, right? Which means going back to my Nernst equation, we are going to be in this scenario, we are basically going to push the reaction forward, right? Which is why we're going to get our electrons to flow until we reach a point where my concentration of ions are equal, right? And once my concentration of ions are equal, right, then we go back to our E naught, which is 0, which means no net flow of electrons, right? Or we could say that the flow of electrons forward, the flow of electrons reverse is equal, so there is no net flow of electrons. And we'll see here, right, that the colors are the same of my two solutions, which also indicates that, yeah, obviously, we've reached equilibrium. Yes, does that make sense? Right? So Nernst's equation is how a concentration cell is built. Make sense? All right. Thank you for listening. Be good and stay tuned for the next one where we talk about how we take these spontaneous reactions and look at them in real life scenarios. All right. Thanks for listening. Be good, and I'll see you soon. Bye.